Hi everyone, we are going to learn about the fourth lab experiment, that is design Verilog HDL to implement binary adder subtractor off and full adder off and full subtractor. In binary adder subtractor, digital computer performs variety of information processing tasks. Among the functions encountered are the various arithmetic operations. A binary adder subtractor is a combinational circuit that performs the arithmetic operations of addition and subtraction with binary numbers. We will develop this circuit by means of hierarchical design. The half adder design is carried out first, from which we develop the full adder. Connecting n full adders in cascade produces a binary adder for two n-bit numbers. The subtraction circuit is included in a complementing circuit. First, half adder circuit. First, let's start with the half adder circuit. Half adder circuit needs two binary inputs and two binary outputs. The input variable designate and added bits. The output variable produces sum and carry. We assign symbol x and y to the two input sum and carry to the outputs. The sum output represents the least significant bit of the sum. The simplified Boolean function for the output can be obtained directly from the truth table. The simplified sum of product expression are sum expression and carry out expression. This half adder is a combinational circuit which adds the two bits and it gives the sum and carry bit as the output. So now let's see what is the logic circuit of this half adder, and for that using the truth table. First of all, let's understand that when we had the two bits, then what are the possible outcomes? So for the two bits there are four different combination, right? So here these 0 plus 0 is equal to 0. That means whenever a and b is equal to 0, then the sum bit and the carry bit both are 0. Similarly, this 0 plus 1 is equal to 1. That means the sum is equal to 1 and the carry bit is equal to 0. Likewise, this 1 plus 0 is equal to 1. That means whenever this a is 1 and the b is 0, then this sum bit is equal to 1 and the carry bit is equal to 0. Likewise, this 1 plus 1 is equal to 0 with 1 has carry. That means whenever both a and b is equal to 1, then the sum is equal to 0 and the carry bit is equal to 1. So this is the truth table of the half adder. So as you can see, this sum output is 1 when a is 0 and b is 1, or when a is equal to 1 and b is equal to 0. So if we see the boolean expression of this sum output, then it is equal to a dash b less a b dash. Similarly, this carry bit is equal to 1 when both a and b is equal to 1. If we see the boolean expression of this carry bit, then it is equal to ab. So these are the boolean expression of the sum and carry. So now let's implement that using the logic gate. So as you can see this expression, the sum output can be implemented using 1 to input XOR gate, while the carry output can be implemented using 1 to input AND gate. So this is the logic circuit of adder, and A and B are the inputs, sum and carry out are the outputs. In full adder, this is a combinational circuit which adds the 2 bits and the incoming carry bit and generate the sum and carry bit as the output. So now let's see the logic circuit of this full adder. And simplified expression of the full adder are the expression of sum and the expression of carry out. For that, first let's see the truth table of this full adder. So here for the 3 inputs we have total 8 combinations, right? So here in this first row, zero plus 0 is equal to 0. That means the sum is 0 and the carry bit is also equal to 0. Similarly in the next row, this 0 plus 0 is equal to 0 and then 0 plus 1 is equal to 1. That means in the second row the sum is equal to 1 while the carry bit is equal to 0. Then in the third row, this 0 plus 1 is equal to 1 and then 1 plus 0 is equal to 1. That means in the third row the sum is equal to 1, the carry bit is equal to 0. Likewise, in the fourth row, the 0 plus 1 is equal to 1 and 1 plus 1 is equal to 0 with 1 has carry. That means in the fourth row the sum bit is equal to 0 while the carry bit is equal to 1. Likewise in the fifth row, the sum bit is equal to 1 while the carry bit is equal to 0. And similarly in the sixth row, 1 plus 0 is equal to 1, then 1 plus 1 is equal to 0 with 1 has carry. That means the sum bit is equal to 0 while the carry bit is equal to 1. Similarly we see the seventh row, then this row 1 plus 1 is equal to 0 with 1 as a carry and then this 0 plus 0 is equal to 0. That means here the sum bit is equal to 1, while the carry bit is equal to 1. And then finally in the 8th row, in 7th row, in this row 1 plus 1 is equal to 1 plus 1 is equal to 0, with 1 has a carry, and then this 0 plus 0 is equal to 0. That means here the sum bit is equal to 0 while the carry bit is equal to 1. Finally in the 8th row, 1 plus 1 is equal to 0, with 1 has carry, and then this 0 plus 1 is equal to 1. That means in the 8th row the sum bit is equal to 1 and the carry bit is also equal to 1. So in this way we got our truth table for the full adder. So as you can see, this sum bit is equal to 1. For the 4 different input combination, and likewise this carry bit is also equal to 1 for the different input combination. So now let's find the boolean expression of this sum bit and the carry bit. This is the boolean expression of the sum bit, sum output. So that is simplified equation for sum can be written as sum output. This is the expression of C output. So we can find the minimal expression using the K map, 3 variable K map. So now this, based on this boolean expression, let's see the logic for this full adder. This is the expression for carry output. Next, half subtractor. Similarly, first start with the half subtractor. Half subtractor is a digital logic circuit that performs binary subtraction of two single bit binary numbers. It is a combination of two input x and y and two output difference and borrow. The different output is the difference between two input bits, while the borrow output indicates whether borrowing was necessary during the subtraction. The simplified sum of product expression are difference and borrow expression. This is the truth table of this half subtractor. So since there are two input So there are 4 possibilities. So whenever both A and B are X and Y are 0, then this difference and barrow output will be equal to 0. Similarly, in the next case, when this x is equal to 0 and y is equal to 1, then the 0 minus 1 is equal to 1, while the barrow will be 1. Likewise, in the third case, 1 minus 0 is equal to 1, that means the difference is 1 while the barrow is 0. And similarly, in the fourth case, this 1 minus 1 is equal to 0, that means both difference and barrow output are 0. So this is the truth table of subtraction. This is the Boolean expression for this different as well as barrow. Based on the Boolean expression, let us see the logic circuit for this of subtraction. So this is the logic circuit of the of subtraction. Then full subtractor. The full subtractor is a combinational circuit that performs subtraction of 2 bits. The circuit has 3 input and 2 outputs. Then x and y are being denote the minute and previous barrow respectively. The 2 output difference and barrow represent respectively. The subtraction usually achieved by adding a complement of subtrahend to the minuend. The simplified expression of the full subtractor are: this is the expression for difference and this is the expression for barrow out. The truth table of this full subtractor. So here for the 3 inputs we have total 8 combinations. So whenever all the 3 input are 0, then this difference and barrow output is 0. Then in next case, zero minus 0 is equal to 0 and the 0 minus 1 is equal to 1 with 1 as barrow. That means in the next row this different output and the barrow output both are 1. Likewise, in the third row, 0 minus 1 is equal to 1 with 1 as a barrow, and then 1 minus 0 is equal to 1. This means in this case also the difference and the barrow output are 1. Then if we move the next case, fourth case, then this 0 minus 1 is equal to 1 with 1 as a barrow, and this 1 minus 1 is equal to 0. That means in fourth case this difference output is equal to 0 while the barrow is equal to 1. Similarly in the next case 1 minus 0 is equal to 1, then 1 minus 0 is equal to 1. In sixth row 1 minus 0 is equal to 1, then 1 minus 1 is equal to 0. Both difference and barrow output are 0. In next 1 minus 1 is equal to 0 while this 0 minus 0 is equal to 0. The difference and barrow output are 0. Likewise in last row in 8th last row 1 minus 1 is equal to 0 and is 0 minus 1 is equal to 1, but in this case we will also have a barrow, and difference output is 1 and a barrow output is also 1. So we can find the minimal expression using the K-map. This is the expression for difference and barrow output. So the Boolean expression of this different output can be written like this. The logic circuit for this different as well as barrow output is this, and the Verilog program for this half adder and the subtractor, and here module in this program module as a keyword, and this is the module name, and this is input and output variables. The input variables are A and B, and then output variables, and finally end with the close with end module, and this is the output of this half adder and a subtractor. And this is the Verilog code for full adder and the subtractor, and this is the module name, and these are the input and output variables, and ABC are the input variables, sum, call, difference, and these are the output variables, and this is the full adder and this is the full subtractor, and finally close with the end module, and this is the output of this full adder and subtractor Verilog code. Thank you.